Welcome back. I hope you finished watching the first video on partial fractions and how that can be a useful method for solving some integrals with rational expressions. So now we're going to talk about the logistic differential equation, which is dy dt equals ky times quantity 1 minus y over L. And so we had exponential growth, which is unlimited. And so sometimes populations, most of the time populations actually are limited by their environment, whether it's predators or not enough food or just physical capacity available. Or maybe it's also, we can use this model for when a disease spreads in a population, right? The disease can only spread to how many people are in the population. So we call that the carrying capacity, which is represented by this constant L. So this is the carrying capacity. And k is our other constant, okay? So this is another constant. And we see that as we graph a logistic differential equation, we are going to get, the curve is going to approach that L, that's its asymptote, as time goes to infinity. And there's another model which you might get to, we might look at next section, called predator-prey model. And so it shows how the predator-prey cycles are kind of in sync with each other. So as the prey goes up, the predator population is going to decrease, and then the prey population will follow that, and it kind of, they're cyclic, and then then the prey population will increase and predator population will follow as it has more food. So those are kind of cool too. We might look at those next section. Okay, example 2. So we're going to solve this logistic differential equation and find the general solution to it. So my equation is dy dt equals ky times 1 minus y over L. So I'm going to go ahead and do my separation of variables. So I get 1 over y times 1 minus y over L dy equals k dt. Go ahead and integrate both sides. And now what we're going to do is we're going to use our good old friend partial fractions to see if we can make that left-hand side simpler. So if I have 1 over y times 1 minus y over L, and that equals, we want to find a over y plus b over 1 minus y over L. Going to go ahead and find a common denominator on the right-hand side. So I'm going to get a times the quantity 1 minus y over L plus b times y all over. And now I have a common denominator on both sides. So I'm going to multiply by that denominator to eliminate it. And I'm also going to distribute a at the same time. So I get a minus ay over L plus by. If I write the left-hand side as 1 plus 0y, I can see that a is going to have to equal 1. And then I get negative a over L plus b times y has to equal 0. So relating coefficients, a equals 1 and 0 equals negative a over L plus b. So if I substitute in that 1 for a and add it to both sides, I get b equals 1 over L. So now if I want to write my integral, I can write that as 2 separate fractions. So I get 1 over y plus 1 over L divided by 1 minus y over L dy equals kt plus c. So now what I'm going to do is I'm going to go ahead and multiply by L on the top and the bottom of that second rational expression. So I get 1 over L minus y dy kt plus c. You can call it c sub 1 because we'll probably have to do another constant later, so might as well. All right, and then I'm going to go ahead and integrate those. So I get natural log of the absolute value of y plus natural log of the absolute value of L minus y equals kt plus c sub 1. Then I'm going to go ahead and combine those into a single natural log. So I get natural log of y over L minus y, the absolute value. Then I'm going to go ahead and put that in exponential form. So I get the absolute value of y over L minus y equals e to the kt plus c1. And then I'm going to roll that plus or minus from the absolute value and the e to the c plus 1 into a new constant. So we'll just call that capital C, as we normally do. If you're still not quite understanding that step, let me know. I'm happy to walk you through it in a little bit more detail. So now we have this, and if I want to solve for y, I get y equals L times c e to the kt minus y c e to the kt. And from there, I'm going to add the y to both sides. So y minus y, y plus c e to the kt equals L c e to the kt. And then I'm going to factor out that y. And then I get 1 plus c e to the kt equals L c e to the kt. Go ahead and divide. So now I get y equals L c e to the kt divided by 1 plus c e to the kt. And then I have this factor of c e to the kt on both the numerator and the denominator. So let's see if we can write that just one time. So I'm going to multiply the top and the bottom by 1 over c e to the kt. And so what happens there is on the numerator, I am just going to get L. And then on the denominator, I can write that as 1 over c. Let's make that a new constant. Let's call it b. So then I get b and then e to the negative kt plus 1. Okay, and that's going to be our general solution where b and L are constants. B, L, and so we have b, L, and k are constants. And this is your general solution to the logistic differential equation. Okay, and that's the standard form we write it in. All right, so let's go ahead and try an example where we're using this. So we got this example with elk. A state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. The growth rate of the elk population is dp dt equals kp times the quantity 1 minus p over 4,000, where p is between 40 and 4,000, and t is the number of years. A, write a model for the elk population in terms of t. B, graph the slope field for the differential equation and the solution that passes through the point 040. C, use the model to estimate the elk population after 15 years. And D, find the limit of the population as t goes to infinity. All right, so if I look at A, we want our dp dt is going to equal kp times 1 minus p over 4,000. Well, we did our general solution before, so we know that our general solution will be p equals L over, I'm just going to write the whole thing out, b times e to the negative kt plus 1. So we have our carrying capacity, our L of 4,000, so I'm going to plug that in. So now I have two more constants I need to find. I need to find the value of b and the value of k. So we are given 2 points to start with. We know that at 0 years I have 40 elk. So if I plug that in, I get 40 equals 4,000 times what? Oh, my goodness. Did it again. I'm so sorry. You can skip ahead until it all refreshes. Okay, here we go. All right, so 4,000 over BE to the negative, I guess it's 0. BE to the 0 plus 1. So I'm going to subtract 1, or I'm going to go ahead and let's see here. So I'm going to cross multiply. So I get, this is just B plus 1. So B plus 1 equals, and then 4,000 divided by 40 is 100. So then I subtract 1 and I get B equals 99. Okay. And then my second point was after 5 years, there were 104 elk. So I'm going to plug that in. So I get 104 equals 4,000 divided by 99 e to the negative k times 5 plus 1. So let's see what I get here. Let me give myself some more space. So I'm going to multiply, and I'm going to get that I have 99 e to the negative 5k plus 1 equals 4,000 divided by 104. Then I'm going to subtract 1 and divide by 99. So I get e to the negative 5k equals 4,000 divided by 104 minus 1, all divided by 99. And then I'm going to take the natural log of that and divide by negative 5. So I get that k equals, you know what, I'm just going to solve for negative k. Might as well, because I know it's negative k in my thing. So if I have negative k, I get that it's the natural log of 4,000 divided by 104 minus 1, all over 99. All of that divided by 5. So negative k is approximately negative 0.194. Once you plug that into your handy dandy calculator. Great. So our final model is going to be P equals 4,000 divided by 99 e to the negative 0.194 t plus 1. Fantastic. Okay, and the next piece was to do the differential equation. For this one, since the differential equation is pretty big, the slope field. Since the slope field is pretty big, go ahead and use that Desmos tool I linked to on Schoology. Okay, so if we find the slope field for that, we're going to go ahead and plug that in, and we're going to make sure we graph the point 040. So 040 is going to be here, and then it gives us the slope field here. So fantastic. All right, next, part C said, estimate the population after 15 years. So I'm going to go ahead and use that model I just found in part A. So I plug in 15 into this. So 4,000 over 1 plus 99e to the negative 0.194 times 15. And I would go ahead and recommend your value that you found for your K. Go ahead and store that value so that you can make sure that you are rounding appropriately when you get to problems where you have to estimate the populations. So once you do that, you should get 626 elk after 15 years. And then part D asked us to look at the limit as t goes to infinity and confirm, we want to confirm it does reach our carrying capacity. And so if I have that, 1 plus 99 e to the negative 0.194 t. Okay, so if I look at this piece here, because I have a negative exponent, that e to that power is going to 0. So my denominator is going to 1 plus 0. So I am reaching 4,000 over 1, which is just 4